Welcome back to the third video about capacitive liquid level measurement. Last time we talked about two methods of how to measure the capacity of your capacitive liquid level sensor. Card here, link in the description. And I told you back then there is a third method which I couldn't show you in that video because I was missing a chip. Now I have these chips. I only need one of them. So we will have a look at the third method in this video. And it's hot again in Germany and I'm a wee bit under the weather, so I try to, that video will probably be short and I will have to defer actually measuring the capacity using a microcontroller to the next video. Anyway, enjoy! The second method we had a look at last time was measuring the charge-discharge curve of an RC element, with the capacitor in the RC element, of course, being our sensor. We saw that, for example, my Bryman multimeter does that by charging and discharging the capacitor to a fixed voltage level. I think it was 500 millivolts, at least that's what I've written here, 500 millivolts. And we also saw if the capacity is increased, of course, the frequency of this charge-discharge cycle increased. And that brings us directly to our third method. Just use that RC element here in some kind of an oscillator and just have a look at the frequency of that oscillator. We can build a very simple oscillator around our RC element by using a logic inverter with a Schmitt-trigger input. Initially, our capacitor is discharged, so we have here a low signal as an input, so the output is high, and over the resistor, the capacitor is charged until we reach the high threshold. Then, of course, the logic input is interpreted as high and our output goes to low, and then we discharge our capacitor via the resistor, of course, until we reach here the low threshold again. So logic input is interpreted as low and our input goes high again and the cycle repeats. I will be using here 1/6 of a 47HCT14. That's the CMOS version of the 4714. And you don't need to bother with our large resistor and small capacitance here with TTL logic or low power Schottky. You have to go for the HCT CMOS version of that logic chip. And that was the chip I hadn't in my lab. I had to order it. And that's exactly what I have on my breadboard here. That's my 47HCT14. You can ignore the Arduino here. It's just supplying the 5-volt rail for that thing. I have here my resistor, and these are the leads to my capacitive sensor. And of course, I attached some oscilloscope probes. Here's how the whole thing is wired, because you cannot really see it on the breadboard. So I get here on VCC my 5 volts from the Arduino, and here I connect to my Arduino ground. So power supply, and then I have a total of 6 of these inverter Schmitt-triggers here inside the chip. Please note the input of the other 5s are all connected to ground, so nothing is dangling in the breeze. And the one I'm using, simply the output goes via a resistor to the capacitor that goes to ground, and the input is connected between my capacitor and the resistor. The oscilloscope probes are connected here and here, so a yellow trace will be measuring the voltage across the capacitor, and the blue trace will be measuring the output voltage of our Schmitt-trigger inverter. That's it. Now let's zoom in on the oscilloscope and fill up our tank with some water. As you can see, our primitive oscillator produces some jitter here, and the frequency is jumping around a little bit. But yeah, it's within a few percent, so that's okay. To be exact, about 1 kilohertz, so a little less than 2%. Let me stop the capture for a second so we can have a closer look at the waveform when the sensor is dry. So we have a discharge here and we have a charge here, and we already see there are some jumps here. Yeah, we will talk about that later. And we also see that our square wave is not symmetrical, okay? So the low is much longer than the high. But anyway, let's see if this is really working. And I'm filling in now some water. And yeah, that's working perfectly. We're at 300 milliliters. I will have to change the time scale. And, oh, yeah. Some water evaporated, obviously. So almost 600 milliliters. Let me change the time scale. Okay, and we're down to about 18 kilohertz. Yeah, we still have these little jumps here, which is interesting, and of course the signal is not symmetric, our square wave, but anyway, it's working, and we got quite a big signal out of here. The frequency we measure at such an oscillator should be some constant K over RC. RC, of course, being our time constant tau of our RC element. And if we multiply that by C and divide it by F, we can calculate from the frequency and the resistor and that constant our capacity. So capacity is equal to K over R times F. So we already measured with my Bryman, that big old chunk, the capacity of our sensor with additional leads last time at dry 50 picofarads and wet 110 picofarads. Now that Beckman Industrial is a little bit more sensitive, so we are here in the nanofarad range, and we are measuring now with nothing connected 2 picofarads. And if I connect the dry sensor, we are measuring, yeah, without all the additional leads, about 18 picofarads. Now let me fill that up to the 600 milliliter line again. Okay, so including the leads, we are here at, let's say, 74 picofarads. With no connection to our multimeter, we measured 2 picofarads, dry 18 picofarads, and wet 74 picofarads. So we can subtract that offset here with nothing connected, and we get to values of 16 picofarads and 72 picofarads. At frequencies, we measured that with an oscilloscope of 56 kilohertz and 18 kilohertz. Now, you can, of course, calculate that constant K from that formula too. You just multiply here by RC, then you get K equals to F times R times C. And when you do that, so in the first case, a K is equal to 56 kilohertz times 1 megaohm times 16 picofarads, you get a K of 0.896, and the unit is hertz ohm farad. But in the second case, so 18 kilohertz times 1 megaohm times 72 picofarads, you get 1.296 hertz ohm farads. Something is not working as expected. Because, that constant should, of course, be constant and not change with the frequency and the capacity. So let's have a closer look at the waveform and find out why our frequency isn't changing nicely and linear with 1 over the capacity. First, I want to find out why our square wave is not symmetrical, not 50-50. Please note that doesn't really influence our constant K or our frequency, but it's good to know why that happens. The upper and lower threshold, when we switch between charging and discharging our capacitor, respectively, the output of our Schmitt-trigger inverter changes from high to low are 1.62 volts and 940 millivolts. The output voltage of our Schmitt-trigger inverter is between 4.82 volts when it's high and 40 millivolts when it's low. The SN47HCT14 datasheet tells us that the positive going threshold is between 1.4 and 1.7 volts. We measured 1.62 volts, so spot on, and the negative going threshold is, depending on the conditions, between 1 volt and 0.9 volts, and we measured 0.94 volts, so spot on again. Now, the high-level output voltage should be between 4.3 volts and 4.49 volts, typical, and we measured 4.82. Well, we don't put a lot of load at the output. These 4.3 volts are for an output current of minus 4 milliamps and 4.5 volts. So, we're golden here too. And the same is true for the low-level output voltage, which should be between, somewhere typical 0.17 and 0.0001 volts, and we measured 0.04 volts. Great. So when we start charging, our capacitor is at 0.94 volts and we charge our RC element with 4.82 volts. That leaves us here initially a charging voltage across the resistor of 3.88 volts. While when we are discharging, initially our capacitor is already charged up to 1.62 volts and we are discharging here over our 1 mega ohm resistor to 0.04 volts, and that's initially a voltage here across the resistor of just 1.58 volts. And that's the reason why the discharging takes much longer than the charging. The voltage is simply different. Larger for charging and smaller for discharging. And if you remember your math of the charging discharging curve of a RC element from the last video, the voltage change over time is proportional to the initial voltage. As I mentioned before, that shouldn't really influence or mess up our nice relationship between frequency and capacity. But as you can see at the beginning of the charging and at the beginning of the discharging, we have these jumps, and these are a problem. With the dry sensor, we see that jump here of about 340 millivolts when we start charging. Please note that this is almost or exactly 50% of our total charge voltage here of 680 millivolts. So that's significant. The jump in voltage here when we start discharging is 280 millivolts. That's still 40% of our total discharge charge voltage, so also very significant. But how do these jumps change when we have a wet sensor? And yeah, so also with changing frequency, of course. So maybe you can hear it. I'm filling up my sensor again. That is my tank. I will have to adjust the time scale in a second. We are at the 600 millimeter line. So here, okay, let me stop and measure that again. Our jump here at the beginning of the charge cycle with a wet sensor is 160 millivolts. That's not even half of the 340 millivolts we saw with a dry sensor who had a much lower capacity. And the jump in voltage when we start the discharge cycle is, aboutish 120 millivolts. Also less than half of the 280 millivolts we measured with a dry, lower capacity sensor. These jumps, of course, mess up our nice math for calculating frequency and stuff, because the math assumes that there are nice, smooth discharging curves with no discontinuities between them. The question arises, why do we have these jumps, and is there a way to avoid them? The thing is, when you are working with RC elements where we have capacities in the picofarad range and resistance in the megaohm range, parasitic effects come into play. For example, our resistor here is not an ideal resistor. It's a carbon film resistor, and these resistors do have parasitic inductance. Yeah, they have that too. But that's not important at the moment. But they also have a parasitic capacitance. And this can be in the order of magnitude of 1 picofarad, a few picofarads, aboutish. So in relation to our capacitor here, when we are dry at 16 picofarads, that's quite a current pulse we can get through this resistor here, which is in that case not acting as a resistor but as a capacitor, and have this voltage jump, that initial voltage jump, until that parasitic capacitance of the resistor is charged and the resistor is really working as a 1 megaohm resistor. Another effect we might experience is that we have here, in this case it's probably flowing in this direction, a leakage current out of the input here of the input of our Schmitt-trigger inverter. And please note that input also has some capacitance. Okay, so that's messing things up too. Having a look into the datasheet of our 47HCT14, we see that the input current or leakage current into the input is typically at plus minus 0.1 microamps. That's a typical value. These are the maximum values. A little error here in the datasheet. And that it has a typical input capacitance of 3 picofarads, which is also not nothing. The typical leakage current here out into our capacitor at 0.1 microamps is probably Not noteworthy because we are usually charging here with a few microamps. So yeah, that's just noise. And the input capacitance here of 3 picofarad, yeah, that just goes parallel to our measured capacitor. So that will just, yeah, offset our measured result by 3 picofarads or so. So yeah, also not a real problem. However, if I try to measure the capacity between two adjacent rows of pins on my breadboard, so yeah, measuring these small capacities is not simple, but we are now with leads at 3 picofarads, and I connect the leads somewhere at some adjacent rows, and we are at 4 picofarads. Yeah, so there we have at least another picofarad of capacitance. And of course our 1 megaohm resistor connecting the input with the output is exactly across 2 parallel traces on the breadboard. Yeah. So our breadboard forms another capacitor parallel to our resistor of also in the order of magnitude 1 picofarad. And now we have here the parasitic capacitance of the resistor 1 picofarad, parallel few picofarads, and parallel to the capacitance of the 2 traces on my breadboard. Also order of magnitude maybe a few picofarad or 1 picofarad. So now we have here several picofarads parallel to the resistor. Each time we change polarity here at the output, delivering a short current spike in or out of our capacitor and making the voltage here at that point jump up and down. All these parasitic capacitances here deliver approximately the same current spike into or out of our measured capacitor when we switch from charge to discharge and vice versa. However, since our measured capacity changes, the voltage jump we see here across our capacitor changes, of course, in amplitude. And that totally messes up our nice relationship between output frequency and the measured capacity. Yeah. It is what it is. When you come, I mentioned that before, in these regions where you are working with picofarads and megaohms, you have to take all these effects into account. And now imagine we are using a more realistic sensor and not such a bulky thing. So typical capacitive sensors for liquid level measurement range maybe between order of magnitude lower, so in the picofarad range. So they might change from 2 picofarads to 5 picofarads instead from 16 picofarads to 74 picofarads. And then you need, if you want to keep the frequency low of the whole thing, or the curve, the charge-discharge curve, reasonably slow, you have to go up here also an order of magnitude. So from megaohms to 10th of megaohms. And things get complicated. All this means you have to take special care when designing such a circuit. When designing the PCB, you should probably avoid parallel traces here between the output and the trace connecting to your capacitive sensor. So trying to minimize that parasitic capacity here. Also, you should choose metal film resistors because they have a lot lower parasitic capacitance than carbon film resistors. Also, the inverter you choose here, you have to consider the leakage current and the capacitance of the input. I mean, the 74 HCT14 is not bad, but you can do better. You could go instead of a Schmitt-trigger inverter, which is really the simple circuit, for the CMOS version of the 555, called by Texas Instruments the LMC 555. And that's a circuit. You really don't need that stuff here. So it's not more parts, okay? And this will actually give you a 50% duty cycle square output. Also, the leakage currents at our reset and threshold pins are typically only 10 picoamps. That's an order of magnitude better than the typically 0.1 microamps or 100 picoamps of our 74 HCT14. Though the LMC 555 will set you back about $5, while you get the SN47 HCT14 below $1. And if you are willing to shell out a few $100, you can get analog comparators and build a Schmitt-trigger circuit around them, and those can offer you input currents, respectively input offset currents of 0.04, respectively 0.02 picoamps. So even several orders of magnitude better than our CMOS 555. And this is the data sheet of the Texas Instruments LMC 7211-N. As I said, you have to dash out a few $100. There's another design aspect I want to talk about. I mean, we are now running with an almost dry sensor at 50 kilohertz. That's a little uncomfortably high for me frequency-wise. The reason being, if you look at that, so that's a long metal rod. What does you remind you of? Yeah, an antenna. So given the transmit power we have here is probably not very high, it's maybe a few microwatts or a few dozen microwatts or so. So it's not very high. But if you are EMI conscious, you notice that the waveform we feed into our antenna with the hard jumps and so on will create a lot of high frequency harmonics. And so that thing is actually, when we run it at higher frequencies, transmitting. And to avoid that, or to minimize that, we should lower the frequency. So let's try some larger capacitor resistors here to lower the frequency a bit. I replaced my 1 megaohm resistor with a 10 megaohm resistor, and you cannot read that here, but we are now, and I changed the time scale, down to 6 kilohertz. I feel much more comfortable with that EMI-wise. That's it for today. I'm sweating and I'm a little bit dizzy. Yeah, I told you in the beginning I'm a little bit under the water. The video got longer than I expected because, yeah, when you start explaining and you see, okay, you need to explain these little drums and the other effects you see when you are working with RC elements with extremely high resistances and extremely low capacitances. Anyway, next time we will actually use the microcontroller here, Arduino Nano Every, and do liquid level measurements with it. Initially probably using that little oscillator here, and later on we will use another technique. Till then, bye!